This is Mr. Craig, and I want to talk about kinetics today. This is the first example, part A, for the kinetics section. When we talk about kinetics, we're talking about reaction rates. One thing that we have to realize that when we're working with the reaction rates or with kinetics is we can never ever look at a balanced equation and determine from the balanced equation how fast or how slow a reaction is. In this first statement that's at the top of the page here, it states that reaction rates can only be determined experimentally. So what I don't want you to do is fall in the trap of saying, wow, there's some really high coefficient values within the balanced equation, so that must mean that the reaction is really fast. Or say that all the coefficients for the balanced equation happen to be 1, so that must mean it's a really slow equation. There's no way that we can look at a balanced equation and know enough about it to determine whether something is fast or slow. So again, reaction rates must be determined by going into the lab, actually doing the experiment, and timing it. Things that we want to time when we're actually looking at the lab is how quickly something appears, one of the products, or how quickly something disappears, one of the reactants. So when we talk about rate, we're talking about the amount of stuff being consumed or produced per unit of time. And the unit of time can be in seconds, it can be in minutes, it can be in days, hours, and so on. But rate is a two-part unit. So it's something, maybe grams, maybe molarity, something over a unit of time. Looking down near the middle of the page here, we have what's called the average rate. We're not too concerned about average rate so much as the initial rate. Later on, when we work on some problems and use natural logs, we won't be so concerned about the rate, but we'll be concerned about where the reaction is at some point in time. The rates, we only want to focus on the initial rate. I'll just leave it at that. However, if you wanted to find the average rate at some point in the reaction, then you may use this equation here where it says that the change in concentration over the change in time would be the average rate. Looking at the graph at the bottom of the page here, you can see that a reaction actually has a deceleration curve and that the reaction does slow down as it nears completion. And think about this. At the beginning of the reaction, we have nothing but reactants and no products, so all the reactants can find each other rather quickly. However, as the reaction proceeds forward and we get near the end, then we have many more products and not so many reactants, so it's very difficult for the reactants to find each other to make the products. So we would expect a reaction to slow down as it nears completion. Looking at the back side of the page, if you wish to plot the slope of these or the average rate at that point in time, you'll notice that at the beginning, at point 1, that the slope is nearly vertical. In other words, that's moving pretty quickly. However, when we get near the end of the reaction, the slope is almost horizontal, which means it's almost stopped. So this is a clear indication that the reaction rate is quickest at the beginning and slowest at the end. Looking over the rest of this stuff, that's pretty much all I want you to know about the first sheet. This is Mr. Craig, and this is examples part 2 for the kinetics, the first day lecture. What I want to talk about in examples part 2 is what type of question you will see on the AP exam and what type of question you'll see on the test. In this example here, or this set of examples, we have an experiment where we have the reactants A, B that form C and D. Now, honestly, we don't even need to see this balanced equation to do these types of problems, and often what I don't want you to do is look at it and say, oh wow, look at that number 2 there. That 2 must mean that there's something really special that's going to take place here. Ignore. If you ever see a balanced equation and a table that looks like this, I would cross that that equation out. I wouldn't even look at it. Oftentimes some people, and we're going to talk about the orders of reactants here in a moment, some people might look at that and say, oh, that's first, or that's a second order reactant. I don't want you to make that mistake. All right, so looking at the table here, which is very important, the experiment 1 through 5, right here, these deal with the different trials. In other words, you'll notice that the concentrations for A are here, and the concentrations for B are in this third column. Now notice that there's no coefficient in front of the concentration of B. We don't care. The balanced equation is to make sure that the number of atoms are the same on both sides. What you will recognize is that in some cases I may leave the concentrations the same in a couple trials. Like in this case for A, I have 2 and 5 are the same, and then for B I have 1 and 2 are the same. This is kind of important. If you're designing a lab, you want to try to have concentrations remain the same while changing other concentrations so that you can find out, ooh, this reaction is really fast if I double it, or it doesn't change when I double it, or it becomes really, really fast when I double it. And again, this is all determined experimentally. In this last column, we have the rates, and again, the initial rate. And the rate in this case is molarity per unit of time, which happens to be second. So molarity per second. We will use this data in part 3, or something that looks like this in part 3, to determine the rate law. And the rate law will be explained here in a second. I'm going to scoot down here to the orders. When we talk about a reactant, it's either a zero order reactant, a first order reactant, or a second order reactant. Now for the AP exam, those are the only 3 orders that we care for a reactant. And what that means is, if you're looking at a zero order reactant, okay, and that's right here, what that's saying is, regardless of what the concentration is, the rate of the reaction does not change. So if I go and double the concentration, the rate remains the same. If I triple the concentration, the rate remains the same. That's for zero order reactants. If I'm looking at a first order reactant, which is right here, if I double the concentration for a first order reactant, then I speed the reaction up twice as fast. If I triple the concentration for a first order reactant, the reaction is now 3 times faster. If I quadruple the concentration, it's now 4 times faster. That is a first order reactant. So again, zero order, you change the concentration, whether it goes up or whether it goes down. That rate remains constant. For a second order reactant, what happens is, if I double the concentration, this is an exponential growth. So if I double it, it's 4 times faster. If I triple it, it's now 9 times faster. If I quadruple it, it's now 16 times faster. So when we are looking at doing these labs, or looking at this data here, we're going to find out what each of these reactants do and how they behave. Some are first order, some are zero order, some are second order. It can only be one of those 3. Now, I can have A be a first order reactant and B be a second order reactant, and that's fine, just as long as they have an order. Okay. And then down here I have how you would represent that. If we're looking at, say, a first order reactant, you have the option of putting a 0 as your superscript, or not showing it at all. Because anything to the 0 power is 1. So if you have a concentration that's a zero order reactant, and when we go and plug it into the data that we're going to be using for this table here, it doesn't change. If I look at a first order reactant, you have the option of leaving it as it's noted there, or you could put a little 1 as a superscript there. However, with the second order reactant, we must show the exponent as a 2. Okay, and that'll become more clear once we actually do the examples in part 3. On the back side of this sheet, I actually have what we're going to do in examples part 3, so if you want to look over that, that's fine. However, I'm going to actually go through this whole sheet when I do an example lab. So I don't really want to read it to you because it doesn't make a whole lot of sense unless you've actually done it. Now, I do want to talk about the rate law. The rate law is something that's very important that you'll always be asked. if you have a kinetics type question here. And what this rate law looks like is an equation that actually has rate to start it off. So the rate law must have the word rate within it. And the rate deals with the rate down here. So we're going to, in the examples part 3, you will pick one of these rates to determine what the k is. And a k is a constant. And the k is a constant for all these trials. Now, what's also cool is once we determine the order, and I have m and n here, you can use x and y, or you can use whatever letters you want. Just don't try to use O or L, things that look like numbers. Why I use m and n, it's what my high school teacher taught me, and that's what my college professor used. I don't think there's any logic as to why. It's just something that's been taught to me. So the rate law will include the word rate. It'll have the constant for the reaction, and then it'll have the order for each of the reactants. Notice there's no products in this. We do not care about the products when we're doing kinetics. We only care about the rate of disappearance when we're doing these types of calculations. Alright, move on to the next video, and I'll actually work out a problem or two here. This is Mr. Craig, and this is examples part 3, where we're actually going to work out a problem, actually work out 2 problems here. What we have here is the reaction where we have ammonium and nitrite reacts to form nitrogen and water. And what I want you to recognize is we have 3 experiments here. Trials. We have 3 trials, 1, 2, and 3, and we have concentrations for the ammonium, and we have concentrations for the nitrite, and we actually have the initial rates. So that data has already been provided for you. From this information, we should be able to find the rate law and the value for the rate constant, which happens to be K. So first of all, what we want to do is we want to determine the rate law, and by doing that, I need to first of all get it so I can start writing. Okay, so the rate law will always include the word rate, and we want to put the constant K, and then what we're going to do is we're going to determine the order for each of the reactants. So I'm going to have M here, and for the nitrite I'm going to look for N. Okay, so that is the rate law, but it's incomplete. When we finish, we're going to have a value for M and N here. So we really don't know what the rate law is yet until we actually do the calculation. And doing the calculation for finding the rate constant, which happens to be K, or right here, will give us the orders for each of these reactants. Alright, so let's do part B, and then we'll come back to part A and finish that up. Alright, what we want to do is we want to find 2 concentrations that are the same for either of the elements, or I'm sorry, of either of the reactants. And if we look at experiment 1 and 2, the concentrations for the ammonium is 0.1, and in trial 1 and trial 2, and then for the nitrite, the concentration is 0.01 in experiment 2 and in experiment 3. So it's up to you to decide which one you actually want to use on that. Alright, so actually we'll start off with experiment 2 over experiment 1. Now what I want to do is I want to find the rates of these 2 experiments first. So what I need to do is check over here. Here are my rates, and I'm going to place the rate of experiment 2 on top here, because what I'm doing is I'm placing the higher of the 2 values on top so that I get a whole number. It makes it a little easier for me. You don't necessarily have to do it that way, but in my experience I found out that that's a little bit easier. So if I look at these 2 values here, and if you need a calculator, that's fine, but 2.70 times 10 to the negative 7 divided by 1.35 times 10 to the negative 7 actually equals 2. What that's saying is that the conditions in experiment 2 are twice as fast as the conditions in experiment 1. So experiment 2 is twice as fast as experiment 1. Alright, now what we want to do, once we know that the experiment 2 is twice as fast, I want to find out what the orders are. So what I'm going to do is I'm going to plug in the values for experiment 2. So I'm going to look at the concentration for the ammonium and the nitrite. And again, we plug in everything from our rate law, which is here. So I'm going to have my K, which I don't know yet. I'm going to calculate it, is equal to, times the concentration of the ammonium, and I don't know what my order is yet, times the concentration of my nitrite, which I also don't know the order for yet, all over K, the constant, times what the concentrations are in experiment 1. So I have 0.100, again, don't know the order, over 0.0050. And what I want to do at this point is I want to cancel out everything that's alike. So M will be the same order, so those can cancel out, and the constant will remain the same. So now what we're left with is the concentration of the nitrite, which is different, and that's okay. It's 0.01 divided by 0.005. What that equals is 2N. So now what we want to do is we have our concentration, which is 2N, is equal to 2. We want to find out what the exponent N is equal to. Well, we already know that our only options for order happen to be 0, 1, or 2. So 2 to what power equals 2? Obviously, 1. So what that means is my order for the nitrite is a first order reactant. Alright, so now let's do the same thing for the ammonium, where we want to use experiment 2 and 3 because the concentrations for the nitrite. Now that we know that the order for that is first order. So what I'm going to do in this case is I'm going to do experiment 3 over experiment 2. And again, I'm basing that on the concentrations that have the same value. So in experiment 3, my rate is 5.4 times 10 to the negative 7. My pen is not working very well. Over the constant, and I have it right here, 2.7 times 10 to the negative 7. And again, if you need a calculator, that's fine. So 5.4 times 10 to the negative 7 divided by 2.70 times 10 to the negative 7 also equals 2. They won't all be just that easy. So now I want to plug in my concentration, so I need to look at experiment or trial 3. So I have my nitrite is, my ammonium is 0.02. So again, the K, 0.200, and I don't know what it is yet. And my concentration for that is 0.0, really, come on, 0.01 to the first over my constant. Come on, really? And the concentration is 0.1. Again, don't know what the concentration is. And this one is the same. Okay, so again, cancel out all like terms. So the K's are gone, those are gone. So now I'm left with 0.2 over 0.1. And again, in this case, 2M. And so 2M is equal to my rate, which is 2. So M is first order. So to write the rate law correctly now, I'm going to have rate is equal to the concentration of my ammonium. Please write my ammonium first order times my nitrite, which is also first order. Right, please. Okay, so now that I know what my rate law is, and this is my rate law right here, I want to calculate for K. So what I need to do is rearrange these variables. So I'm going to have rate over the concentration of the ammonium over the concentration of the nitrite is equal to K. K. So now what I do is I come back to my data and I pick one. It doesn't matter which experiment or which trial you pick, just as long as you're consistent. So if you want to pick experiment 3, I don't care. We want to put the rate, which is 5.4, which is 5.4 times 10 to the negative 7. And we do care about our units here, so it's molarity per second. And our concentration is, for the ammonium, is 0.2, and the nitrite is 0.01. Trying to remember that. So 0.2, and again, molarity to the first power, and the nitrite is 0.01. 1 to the first power, and that equals, I'm trying to remember, 2.7 times, come on, right, times 10 to the negative 4. And my unit for this, molarity cancels out, so I'm left with 1 over seconds molarity. So there's my K. Alright, I'm going to stop this video and I'll do example part 2 in the next video. Hopefully this pen will work a little better for me. This is Mr. Craig and I'm going to do example part 2. So I'm going to flip the page over here. And in example part 2, very similar to example number 1, we have 4 trials in this case here, and we have the reaction where we have nitrogen monoxide reacts with bromine to form NOBr. Again, we really don't care about the balanced equation, so we never want to get distracted by that. So let's start off with the rate law. So we know that the word rate would be nice if they would write it, is equal to the constant K, and we have our NO, and we don't know what the order is yet, so I'm going to leave that blank. And then bromine, and I don't know what the order for that is yet. So when we finish, we'll put in the orders on the top here. Alright, just like in the first example, pick 2 experiments. Ideally, we want to try to make the concentrations the same for one of the reactants first to start off with. So if you look at experiment 1 and experiment 3, the nitrogen monoxide has the same concentrations there, so it's a good one to start off with. So let's compare experiment 3 to experiment 1. And again, you don't have to start with this one, and would love for this thing to write. And in experiment 3, we deal with the rates first. So in experiment 3, we have 60 over 24. Ugh. 24, and 60 divided by 24, I believe, is 2.5. Okay? So what that is saying is that experiment 3 is 2.5 times faster than experiment 1, based on the concentrations that are given there. Alright, so let's find out what the order of one of these happens to be. So we go ahead and plug in the data from experiment 3. So again, K, and the concentration for the nitrite in experiment 3 is 0.1, and we don't know what the order is yet, so we'll determine that. And for the bromine, it's 0.5, and we don't know what that is either. All over. Really? Come on. I'm going to move that up a little bit. Maybe that's the problem. Also 0.1. Nope, that was not the problem. And in experiment 1, that is 0.2. Okay. So again, cross off anything that is the same. So the K's, really, come on. K's are the same, these are the same. So now we have 0.5 divided by 0.2. So again, that is 2.5 to the n power. So what that means is 2.5 to the n is equal to 2.5. Therefore, n is equal to 1. Write it, please. So the bromine is a first order reactant. Okay, so we got that one out of the way. All right, so let's come up to the data and let's find where the bromine has two concentrations that are the same. Well, it looks like in experiment 1 and 2 or in 3 and 4. So it's your choice. You get the pick. Let's go with 2 and 1. So in experiment 2 over experiment 1, my rates, and again I want to look at my rates, it's a 150 over 24. Okay. And 150 divided by 24, I believe, is 6.25. So what that's saying is that experiment 2 is 6.25 times faster than experiment 1. Okay. So let's plug in our values there. So in experiment 2, we have concentration 0.25 and 0.2. 0.25, and we don't know what M is yet. And 0.2, and that is a first order reactant. And then in experiment 1, we have 0.1 and 0.2. 0.1 and 0.2. First order as well. So again, cancel out anything that's alike. So these guys are gone, K is gone, constant remains the same. So we have 0.25 over 0.1, which is 2.5 to the M. And so now we have our rate, which is 6.25, is equal, please be equal to 2.5. Come on. 5 to the M. So M is equal to what? Now, some of you are going to stumble on this and say to yourself, how in the world are we supposed to figure that out? Remember, your only options for order are 0, 1, and 2. So if you're not sure, get your calculator out and type it in. So if you do 2.5 to the 0, then that has to be 1. If you do 2.5 to the first power, then that has to be 2.5. If you do 2.5 to the second power, or squared, then we have our order that we're looking for. So M is a second order reactant. What are you doing? Hang on here, sorry guys. Come on. It's a second order reactant. So our rate law will look like this, where rate is equal to K times the concentration, what is that, NO? Yeah, NO and bromine. NO, which we just calculated, is second order, and the bromine is first order. So there's our rate law for this reaction. Now again, the question was wanting us to determine the value of the rate constant, so we have to calculate what K is. So again, let's rearrange these variables so that we have K all by itself. We're going to have NO squared over bromine to the first power is equal to K. And again, you get to pick which experiment you want to use. Does not matter. Again, K is going to be constant for all of these. So, which one did we use last time? 1? Yeah. Let's go with number 3. So number 3, The rate is 60. The rate is 60 molarity per second. And the nitrogen monoxide is 0.1. So 0.1 squared. So we must square that if it's second order. And then the concentration for the bromine is 0.5. And that also is molarity, but it is a first order reactant. So before we get a number here, let's find out what our unit is. So our unit, the molarity is going to cancel out. We have molarity squared and seconds on the bottom, so we're going to have 1 over molarity squared per second. I'm not sorry, or not per second, but molarity squared second. That's a dot there. And then let's type this in on our calculator. So 60. So that's, I think that's 12,000. So 1.2 times 10 to the 4. And there's our value for K. Not too difficult. I'm really hoping that this year, and again, when I made this video, it's in 2011, I'm hoping that this shows up on the AP exam. It's been a couple years since we've seen a kinetics problem like this, and we are overdue. So this would be a type of problem that you would find in either question number 2 or question number 3 on the calculator portion of the AP exam. I hope this video has helped.